actually sees images. Today, we're diving into the fascinating world of computer vision, where machines interpret pictures much like our own eyes do, but with a digital twist. We'll explore how AI breaks down images into pixels, extracts features, and uses powerful tools like convolutional neural networks, or CNNs, to make sense of what it sees. By the end of this journey, you'll have a clear understanding of how AI processes visuals, step by step, from raw data to meaningful insights. Let's get started by looking at the very basics: pixels. Every digital image is made up of tiny dots called pixels. Think of pixels as the smallest building blocks of a picture, each holding a specific color value. When you zoom in on a photo, you'll notice it becomes a grid of colored squares. These pixels are arranged in rows and columns, forming the complete image. For AI, understanding an image starts with reading these pixel values. Each pixel's color is usually represented by numbers, often in the form of RGB values, which stand for red, green, and blue. Let's see how AI reads and interprets these pixel grids. When an AI system receives an image, it doesn't see a cat or a tree, it sees a matrix of numbers. Each number represents the intensity of color in a pixel. For example, a grayscale image uses 1 number per pixel, while a color image uses 3 numbers for red, green, and blue. These numbers are organized in a grid, just like a spreadsheet. The AI's first step is to process this grid, analyzing the values to find patterns. This raw data is the foundation for all further image analysis, setting the stage for feature extraction. Once the AI has the pixel grid, it begins searching for patterns. These patterns could be simple, like edges or corners, or more complex, like textures and shapes. The process starts with basic mathematical operations that highlight differences between neighboring pixels. For example, if there's a sharp change in color, it might indicate an edge. By detecting these changes, AI starts to build a map of important features in the image. This is the first step toward understanding what's actually in the picture. Features are the key details in an image that help AI recognize objects. Think of features as clues, like lines, curves, or specific textures, that stand out from the background. In the early stages, features are simple, such as straight lines or color changes. As the AI processes the image further, it combines these simple features into more complex ones, like shapes or even parts of objects. The ability to extract and understand features is what allows AI to distinguish a cat from a dog, or a car from a tree. Feature extraction is the process where AI identifies and pulls out the most important parts of an image. This step is crucial because it reduces the amount of data the AI needs to process, focusing only on what matters most. For example, instead of analyzing every single pixel, the AI looks for patterns that are likely to represent edges, corners, or textures. These extracted features are then used in later stages to help the AI make sense of the image and identify objects within it. Now, let's talk about convolutional neural networks, or CNNs. CNNs are a special type of artificial neural network designed specifically for processing images. They're inspired by the way our brains process visual information. CNNs use layers of filters to scan images, picking out features at different levels of complexity. This makes them incredibly powerful for tasks like image recognition, object detection, and even facial recognition. Let's see how a CNN works, step by step. CNNs process images through a series of layers, each with a specific job. The first layer looks for simple features, like edges or color changes. As the image moves through deeper layers, the CNN combines these simple features into more complex patterns, such as shapes or textures. By the time the image reaches the final layers, the CNN can recognize entire objects. This layered approach allows CNNs to handle complex images with impressive accuracy, making them the backbone of modern computer vision. The heart of a CNN is the convolution operation. This involves sliding a small filter, or kernel, over the image to detect specific patterns. Each filter is designed to highlight a certain feature, like a vertical edge or a corner. As the filter moves across the image, it creates a new map that shows where that feature appears. By stacking multiple filters, the CNN can detect a wide range of features, building a detailed understanding of the image. Filters are small matrices that scan the image for specific patterns. Each filter creates a feature map, which highlights where certain features are found in the image. For example, one filter might detect horizontal lines, while another finds corners. By combining the results from many filters, the CNN builds a comprehensive map of the image's features. These feature maps are passed to the next layers for further analysis, helping the AI understand the image in greater detail. After convolution, CNNs use pooling layers to simplify the data. Pooling reduces the size of the feature maps, making the network faster and less likely to overfit. The most common type is max pooling, which takes the highest value from a small region of the feature map. This helps the CNN focus on the most important features, ignoring minor details. Pooling is a key step in making CNNs efficient and effective for image analysis. Activation functions are mathematical formulas that help CNNs decide which features are important. After each convolution or pooling step, the activation function transforms the data, introducing nonlinearity. This allows the network to learn complex patterns, not just straight lines. The most common activation function in CNNs is ReLU, which stands for rectified linear unit. It simply turns all negative values to zero, making the network faster and more efficient. CNNs become more powerful as we add more layers. Each new layer learns to recognize more complex features, building on the information from previous layers. Early layers might detect simple edges, while deeper layers can identify shapes, textures, or even entire objects. This hierarchical structure is what makes CNNs so effective for image recognition. The deeper the network, the more detailed its understanding of the image. Training a CNN involves showing it thousands or even millions of labeled images. The network adjusts its filters and weights to minimize errors, gradually learning which features are most important for recognizing objects. This process is called supervised learning. Over time, the CNN becomes highly skilled at identifying patterns and making accurate predictions, even on images it has never seen before. During training, CNNs use a loss function to measure how far their predictions are from the correct answers. The goal is to minimize this loss by adjusting the network's parameters. Optimization algorithms, like stochastic gradient descent, help the network find the best settings. This process is repeated over many cycles, or epochs, until the CNN achieves high accuracy. Loss functions and optimization are essential for teaching CNNs to see images effectively. After training, it's important to test the CNN on new images it hasn't seen before. This helps ensure the network isn't just memorizing the training data, but actually learning to recognize patterns. Validation and testing involve using separate sets of images to check the CNN's accuracy. If the network performs well, it's ready for real-world applications. If not, adjustments are made to improve its learning. One of the main uses of CNNs is image classification. This means sorting images into categories, like identifying whether a photo contains a cat, a dog, or a car. The CNN analyzes the features it has learned and compares them to known categories. If the features match those of a cat, for example, the network labels the image accordingly. Image classification is used in everything from photo organization to medical diagnosis. Beyond classification, CNNs can also detect and locate objects within an image. Object detection involves drawing boxes around specific items, like people, cars, or animals. The CNN scans the image, identifies features that match known objects, and marks their positions. This technology is used in self-driving cars, security systems, and many other fields where finding objects in images is crucial. Image segmentation takes object detection a step further by dividing an image into regions based on what's inside. Instead of just drawing boxes, the CNN labels each pixel as belonging to a specific object or background. This creates detailed maps that show exactly where each object is. Image segmentation is important in medical imaging, robotics, and any application where precise object boundaries matter. Transfer learning allows AI to use knowledge gained from one task to help with another. In image analysis, a CNN trained on millions of images can be adapted to new tasks with less data. This saves time and resources, making it easier to build powerful image recognition systems. Transfer learning is widely used in practice, especially when labeled data is limited. Better understand how CNNs see images, researchers use feature visualization. This technique shows which parts of an image activate certain filters in the network. By visualizing these activations, we can see what the AI is focusing on, like edges, textures, or specific shapes. Feature visualization helps improve network design and interpretability, making AI systems more transparent. Despite their power, CNNs face challenges in understanding images. Variations in lighting, angle, or background can confuse the network. Sometimes, small changes in an image can lead to incorrect predictions. Researchers are constantly working to make AI vision more robust and reliable, using techniques like data augmentation and adversarial training to improve performance. Data augmentation is a technique used to make CNNs more robust. It involves creating new training images by slightly altering existing ones, rotating, flipping, or changing colors. This helps the network learn to recognize objects in different conditions, improving its accuracy on real-world images. Data augmentation is a simple but powerful way to boost the performance of AI vision systems. Adversarial examples are images that have been subtly altered to fool AI systems. These changes are often invisible to humans, but can cause a CNN to make mistakes. Understanding and defending against adversarial examples is a major area of research in AI vision. By making networks more resilient, we can build safer and more trustworthy AI systems. Explainable AI aims to make the decision-making process of CNNs more transparent. By understanding which features the network uses to make predictions, we can trust its results more. Techniques like feature visualization and saliency maps help reveal the inner workings of AI vision, making it easier for humans to interpret and validate the network's decisions. AI vision is used in a wide range of real-world applications. From facial recognition in smartphones to automated quality control in factories, CNNs are making a big impact. They help doctors analyze medical images, enable self-driving cars to navigate safely, and power search engines that find images online. The possibilities are growing every day as AI vision technology advances. Facial recognition systems use CNNs to identify people in photos or videos. The network analyzes facial features, such as the distance between eyes or the shape of the nose, to create a unique digital signature for each person. This technology is used in security, unlocking devices, and even organizing photos by person. Privacy and ethical concerns are important considerations in this field. In healthcare, CNNs help doctors analyze medical images like X-rays, MRIs, and CT scans. The network can spot patterns that might indicate diseases, such as tumors or fractures, often faster and more accurately than humans. This technology assists doctors in making diagnoses and planning treatments, improving patient outcomes and saving lives. Self-driving cars rely on AI vision to understand their surroundings. CNNs process images from cameras, identifying other vehicles, pedestrians, traffic signs, and obstacles. This information is used to make driving decisions in real time, helping cars navigate safely and efficiently. AI vision is a critical component of autonomous vehicle technology. In manufacturing, CNNs are used for automated quality control. Cameras inspect products on assembly lines, checking for defects or irregularities. The AI can spot tiny flaws that might be missed by human inspectors, ensuring high standards and reducing waste. This technology helps companies deliver better products to customers. Image search engines use CNNs to find pictures that match a user's query. The network analyzes the features of each image, comparing them to the search terms. This allows users to find similar images, identify objects, or even search by uploading a photo. AI vision makes searching for images faster and more accurate than ever before. AI vision isn't just about analysis, it's also used in creative fields. CNNs can generate new images, transform photos into artwork, or even help artists design unique pieces. By learning from thousands of examples, AI can mimic different styles, blend images, or create entirely new visuals. This opens up exciting possibilities for art and design. While CNNs are powerful, they have limitations. They require large amounts of labeled data to train effectively, and they can struggle with images that are very different from their training set. CNNs can also be fooled by adversarial examples or unexpected changes in the environment. Researchers are working to overcome these challenges with new techniques and architectures. The field of AI vision is constantly evolving. New architectures, like vision transformers and capsule networks, are being developed to address the limitations of CNNs. These models offer new ways to process images, often with greater flexibility and accuracy. As research continues, we can expect even more powerful tools for understanding and generating images. As AI vision becomes more widespread, ethical considerations are increasingly important. Issues like privacy, bias, and accountability must be addressed to ensure that AI systems are used responsibly. Developers and users alike need to be aware of the potential impacts of AI vision, working together to create fair and trustworthy technologies. AI vision systems often process sensitive images, raising concerns about privacy. It's important to protect personal data and ensure that images are used only for their intended purposes. Techniques like anonymization and secure data storage help safeguard privacy, while regulations guide the ethical use of AI vision technology. Bias can occur in AI vision if the training data isn't diverse enough. This can lead to unfair or inaccurate results, especially for underrepresented groups. Addressing bias involves using diverse datasets, testing for fairness, and regularly updating models. Ensuring fairness in AI vision is essential for building trustworthy systems. The future of AI vision is bright. As technology advances, AI will become even better at understanding and generating images. We'll see new applications in fields like augmented reality, robotics, and entertainment. With continued research and responsible development, AI vision will play a key role in shaping the way we interact with the world. Augmented reality, or AR, combines real-world images with digital information. AI vision helps AR systems recognize objects and environments, overlaying useful data or graphics. This technology is used in gaming, navigation, and education, creating immersive experiences that blend the physical and digital worlds. Robots use AI vision to navigate, interact with objects, and perform tasks. CNNs help robots recognize their surroundings, avoid obstacles, and manipulate items with precision. This technology is essential for automation in factories, warehouses, and even homes, making robots more capable and adaptable. AI vision is transforming entertainment and media. From automatic tagging of photos to creating special effects in movies, CNNs are making content creation faster and more creative. AI can even generate new music videos or help editors find the perfect shot, opening up new possibilities for storytelling and production. AI vision is becoming part of our daily lives, often in ways we don't notice. From unlocking phones with a glance to sorting photos by location or event, CNNs are working behind the scenes. As the technology improves, we'll see even more convenient and helpful applications, making our lives easier and more connected. If you're interested in learning more about how AI sees images, there are plenty of resources available. Online courses, tutorials, and research papers can help you dive deeper into topics like CNNs, feature extraction, and computer vision. Whether you're a beginner or an expert, exploring AI vision is a rewarding journey. Let's recap what we've learned. AI sees images by breaking them down into pixels, extracting features, and using CNNs to recognize patterns. This technology powers everything from facial recognition to self-driving cars. While there are challenges and ethical considerations, AI vision continues to evolve, opening up new possibilities for the future. As we look to the future, AI vision will become even more advanced and integrated into our lives. With ongoing research and innovation, machines will gain a deeper understanding of the world through images. By combining technical progress with ethical responsibility, we can ensure that AI vision benefits everyone and continues to inspire new ideas and solutions.